with that, by welcoming you, I really take off. So let me welcome you again to our today's lecture. And what we do today is we once again talk about the Polyakov action and the equations of motion following from it. Okay. All right. So with that, let me just briefly recap that the action is minus d by 2 d2 sigma h alpha beta g alpha beta, and now we vary this action in such a manner that and if we do that, we keep x mu fixed, which means delta x mu we take as 0. So it means that we set this equal to 0. So the response of the variation of this action is, while keeping x mu fixed, that means we study its variation with respect to the auxiliary field h alpha beta, and if we do that, then what we obtain is delta s is minus d by 2 d2 sigma square root of minus h delta h alpha beta g alpha beta minus 1/2 h alpha beta h gamma delta g gamma delta, and we call this guy as T alpha beta. So we define T alpha beta, or we construct T alpha beta in this manner. So this is then the T alpha beta, and it's in fact this is the energy momentum tensor. And here now we have separately studied and this T alpha beta, we call it as the energy momentum tensor because it has all the properties of energy momentum tensor, which is defined as the response of the action S when it is varied with respect to the field h alpha beta, keeping x mu fixed. Okay, so now for this object we have separately proved this to be equal to minus 2 omega a function of sigma alpha into h alpha beta. So if we do that, then minus square root of h into minus 2 omega h alpha beta T alpha beta. And what we know is that this is our one of the gauge parameters of the theory, omega. So omega, which is a function of sigma alpha, which means tau and sigma. So this is one of the local gauge symmetries of the theory. which is responsible for the conformal invariance or the bi-invariance of the theory. And now this object is non-zero, and therefore this has to be 0. And we have seen that in fact H alpha beta, P alpha beta is delta alpha alpha, and this is equals to not delta but T alpha alpha, and this is equal to 0. So this is the trace of the energy momentum tensor, and the trace of the energy momentum tensor T alpha alpha, it vanishes. Okay, so we have already done so far, or we are done so far. Now, so the equations of motion for the our action, Polyakov action, we obtain through the variation of, when we obtain through the variation of H alpha beta, we obtain that this T alpha beta, so the equations of motion for the H alpha beta are obtained. Yeah, please welcome that we set T alpha beta equals to 0, and we have essentially tried to recap some of the basics from our previous lecture so far, and not really done anything new so far. So the equations of motion obtained from the variation of H alpha beta, the auxiliary field, are just obtained as T alpha beta. We will obtain them in the component form also, and we will see what the role they play in our string theory. They play a very important role. Okay, and now this is our T alpha beta, and this is our equation of motion that we obtain, which means we have to set this equals to 0. So which means 0 equal to T alpha beta is G alpha beta minus 1/2 of H alpha beta H gamma delta G gamma delta. And if I save some of my steps, this equals to 0 implies this equals to this. Okay, so this T alpha beta equals to 0 implies this, and this is nothing but H dot G, the scalar product of H and G. So we notice that G alpha beta is proportional to H alpha beta, or H alpha beta is proportional to G alpha beta. Now so if I set beta equals to 1, then this would be equal to G alpha beta, and beta equal to 1 is called as the conformal gauge. So the two are proportional to each other. In any case, H is proportional to G, and if we set the proportionality factor equal to 1, which means, and whenever we do such a thing, it implies that we are making use of the one of the case degrees of freedom of the theory. Our theory has 3 case degrees of freedom, and which we can use. So this is one of them. And so in this case, H is then equals to G. And now let me just keep the action and let me erase all this. So then this is a very important result that we have obtained. And now, okay, now our next point is to handle this guy H alpha beta. So we like to concentrate on, because H alpha beta in general is the auxiliary field. This is also the metric tensor of the word sheet. Okay, so in general this should describe a curved manifold. Okay, can one make use of the case degrees of freedom of our theory to transform it into a flat metric? And how can we do that? Very good. So H alpha beta or H alpha beta is H beta alpha and H, okay,